Ladies, gentlemen, and everybody outside and in between. Today, let's talk about something huge. Something with a diameter of 8.5 kilometers. That's right, your mom. The location, Switzerland. Land of cheese, yodeling, and remaining neutral while all the neighbors kill themselves. But aardvarks, marmots, and animal Gerson and Heidi are not everything that you can find in the Swiss Alps. On the border to France, next to Geneva, there is quite something different. The LHC, Large Hadron Collider, an oversized, underground, donut-shaped fridge used to smash hadrons together. The LHC is the world's largest and most powerful particle accelerator. Built between 1998 and 2008, it is only the last element of a chain of machines that boost particles to increasingly higher energies. We want to do that because of an underlying and utter hatred for hadrons, and to study the fundamental behavior of quantum particles. That all sounds really cool and futuristic, but what exactly are hadrons, and why would we want to smash them together? To understand that, we need to take a quick dive into physics. All things are made out of atoms, and all atoms are made of protons, neutrons, and electrons. And all protons and neutrons are made out of quarks. Next to quarks, there are also a whole lot of other particles that make up the universe. We want to know more about these quarks, but there's one slight problem. They only exist in pairs of two or more hadrons. To separate them, physicists do the only sensible thing that one can do in such a situation. They smash them together at the highest possible energy. In such a crash, many quantum particles are formed that can be measured and studied. But did you notice how I said highest possible energy and not highest possible speed? That is, because of special relativity reasons, speed is limited, but one thing is not. Power multiplied by time. Energy. Energy is unlimited. And just like the little greedy shits that they are, a particle can consume an unlimited amount of energy. But after a point, the additional energy only yields minimal additional speed. Again, thanks to special relativity reasons. For example, a particle in the LHC with an energy of 450 gigaelectronvolts moves at the speed of 0.999997828 times the speed of light, and one with an energy of 7000 gigaelectronvolts at a speed of 0.999999991 times the speed of light. Now, with the basis covered, let's move on to the fun part. How to commit hadron genocide. The complex at CERN deploys a succession of machines to boost its particles to these extremely high energies. Let's look at one example proton to visualize the process. After the poor proton, let's call him Pete the proton, is forcefully taken from his family, he gets accelerated by line 4 to an energy of 50 megaelectronvolts, then injected into the PS booster, where he gets accelerated to 1.4 gigaelectronvolts, and passed on to the proton synchrotron, where Pete is accelerated to 25 gigaelectronvolts and sent to the super proton synchrotron, where he is accelerated to 450 gigaelectronvolts. And finally, he gets injected into the LHC. Here, Pete and his fellow protons are injected in both clock and anti-clockwise fashion and accelerated over 20 minutes to 6.5 teraelectronvolts. They circulate here for hours under normal operating conditions. Now, after being passed around more than a million memes on Facebook, it is time for Pete to die. The proton beams cross on specific locations, where there can be up to 1 billion collisions per second. The scientist's job is to observe and categorize all the particles created in the collision. To do that, there are machines, called experiments, installed at the points where the collisions take place. In total, there are 9 experiments installed at LHC. They are installed in huge underground caverns and have, let's say, interesting acronyms and enormous potential for futuristic album covers. Following this logic, a better name for the International Space Station would be AS. Moving on. How exactly are the particles accelerated in the first place? This gets handled by radio frequency cavities, or RF cavities. They use strong electromagnetic fields to accelerate the beams by changing polarity in the right moments. These cavities operate at 4.5 Kelvin. That's crazy cold. Surprisingly, this is not the coldest place in the LHC. The dipoles, giant magnets, 15 meters in length, used to keep the particles inside our tracks, use superconducting electromagnets that operate at 1.85 Kelvin, a temperature colder than outer space. These temperatures are achieved with a cooling system of liquid helium that effectively makes the LHC the largest refrigerator on Earth. But not only are the dipoles cool, they are certainly also in the heavyweight category when it comes to power. They provide a very high field strength of 8.3 Tesla over their entire length, therefore keeping the particles inside our tracks and allowing operation. Oh, what's that? The time is almost up? Well, then what did we learn today? I let that to the viewer to decide. Sleep well and RIP Pete.